Hello everybody and welcome to session number 21 of my lecture on statistical energy analysis and hybrid methods. Today you will learn exactly why we need this hybrid method, so to say the combination of SEA and finite element systems. And we will also talk about what are the detailed steps of this analysis, because they are quite complicated, but this is what we need if we have a combination of both random and deterministic subsystems. Later, you will learn about a lot of examples and details, but here we just briefly introduce the theory and the single steps of this analysis. So why do we need it? First of all, we have to recommend some details of our first session. I mean, when we do a vibroacoustic analysis, we talk about a frequency range of 20 to 20,000 hertz. That means you have up to 3-4 hours of magnitude to cover, 3 orders of magnitude to cover. In the whole frequency range, you cannot be sure that everything is clearly deterministic or every subsystem is clearly random. In the mid-frequency range, you will have the situation that some subsystems are already random and others are not. So that means we need a method to combine both, definitely in the mid-frequency range. Sometimes this fact was called the so-called mid-frequency gap, because finite element method is a well-known application of Melman simulation method in acoustics, and the same is true for SEA. But what happens when we have this intermediate situation? Good. However, so in a full audible range, and to cover this, we need something, and we need a theory that could deal with everything. Deal with the deterministic part and deal with the SEA part, or in the combination. By the way, this is why this discussion about if SEA is a better method than FEA is completely ridiculous. There is no better or worse, there's just the right frequency range for the right application. Good. So, how do we address that? And I think I would like to come back to the idea of ensemble averaging. And we start with a kind of academic system. And we use the expected value, specific is mean value or expected value of the mean value of the cross-spectral density on this academic system. Just imagine we have one deterministic part here in the middle. There's a random excitation, could be from the outside. We have some deterministic excitation, and we have connected SEA subsystem, and we have two SEA subsystems that are connected among each other. The connected subsystem will definitely change the stiffness of the deterministic one. And on top of that, the reverberant fields in the random systems will create some loading on the deterministic subsystem. So how do we handle this filtering procedure? We start with the easy one, with the mean value. If you take the mean value out of this whole subsystem, the only thing that is remaining is all the deterministic part. So that means at the end of the day, when we take the mean value of several representation of this subsystem that eat all the loads, the only remaining thing is the deterministic force and the response of this subsystem to this deterministic force, plus the impact of the connected SEA system. And as shown in the previous sessions, the main impact of SEA subsystem is that we create a radiation stiffness. We connect a free field radiation stiffness onto this. But this is the only change, and obviously some resulting power flow that goes outside due to this radiation, obviously. When we take the cross-spectral density of our global system, the situation is slightly different. We get everything. We get the deterministic subsystems and all connected random subsystems and all the loads that are there. And we get, let's say, we get a combination of the deterministic response and all the random loads and all the power flow that is in the subsystem that is included in this cross-spectral density random response. Okay, so how do we combine such systems? What is clear is that we have our deterministic stiffness matrix, which is here encountered and denoted by this kind of mesh type. And this is described by a dynamic stiffness matrix. And we have several, let's say, SEA subsystems that are connected to it. And those stiffness matrices have to be connected to form the total set of it, obviously. So regarding the excitation, we have two more or less different kind of excitation. We have the external force, which comes from the outside. This is here on top. And we have the reverberant forces. Those are the forces that are created by the reverberant field in the random subsystems. We can further separate the external force into the deterministic ones and the random ones. And this would give those three forces. So just some remarks. What is it? I mean, again, the external forces are a combination of the deterministic and random one. This deterministic example are typical coherent forces. It could be a rotating machine or something that is clearly defined. Random forces could be turbulent boundary layer, a diffuse sound field from some other creation, ran on the roof, jet noise, whatever. At least something that is created by a random process. And we have the reverberant forces, and those are the created that comes from the reverberant field in the connected SEA subsystem. What is clear is if we take the mean value of this, all the reverberant fields will vanish. The only remaining force that will stay is the deterministic force denoted here by this force arrow. Good. So next step, we have a look into the ensemble average of the classical mean value, the linear state variable. And it means if we take here the random, the first, as mentioned, the total stiffness is created by by the stiffness matrix plus the connected random systems, and we have the external forces, which are and plus the reverberant force. Now let's assume that we take the ensemble average of several subsystems, and there's this is the important step. All the SEA matrices by the, let's say, ensemble averaging process are converted into the radiation, the free field radiation stiffness, and this forms the total stiffness matrix. So the main impact in the clearly deterministic world, again, it was shown also before, is that the stiffness matrix has to be changed slightly because we are no longer in a vacuum. We have some radiation stiffnesses that slightly change the dynamic behavior of our deterministic system, but that is the only change. And the force that has to be considered, the only force that has to be considered, is a deterministic one. Okay, now let's see what we have to do to calculate the ensemble average of regarding to all the reverberant loads, also to calculate the cross-spectral density. As you know, and we start doing just the inversion, so that means the response, the displacement response of a generic displacement coordinates is given by the inverse of the total stiffness matrix multiplied by all the possible loads. We have derived in the earlier session that this is that the response to random load is also defined by the cross-spectral density matrix given by this expression here, and then we come back to our famous triple matrix expression. So left and right inverted total stiffness matrices and the cross-spectral force density in the middle. So quite a complex configuration. So we can separate the random forces, and then we have all the external forces and the reverberant ones. And again, we use this extremely important quantity, the diffuse field reciprocity, which is replacing this by the reciprocity relationship. And that's a good thing. We have quantities that we already need, because the direct field radiation stiffness is something that we need for the radiation, and we can reuse it due to the diffuse field reciprocity again for the excitation. But then we need the energy and the modal density of the connected subsystems. So far, so good. So this is more or less the magic project. So keep in mind, we have considered the deterministic response to the deterministic part. So this is that we figure out what is the the response of our remaining deterministic subsystem in the middle. And then we take care about all the random subsystems, and then we know what are those subsystems creating for kind of loading onto our deterministic subsystem. Something that is not as specifically mentioned, but definitely also there. I mean, all the SEA parts, so to say, all the power flow that takes place here from, okay, this is a single one, but the power flow, or the energy in those subsystems, this is just solved by solving the classical statistical energy of the SEA matrix. Plus the power that was radiated from the deterministic subsystem into the SEA subsystems. Good. So what are the single steps of the hybrid workflow? And I've summarized it here like that. These are mainly 5 steps that will be later described in detail. First of all, we set up all the matrices. The stiffness matrices comes from some FE solver or whatsoever. We need the description of our subsystem, and then we create our junction. Next step is to set up the final matrices. That's mainly the total stiffness matrix, and for those we need all the direct field variation stiffnesses into each connected subsystem. Then we take care about the external loads. So it is the cross-spectral density of specifically random or deterministic load and the power input into the SEA world. Then we solve the finite element equation, the SEA equation, and then we solve all the loading that comes from the SEA subsystem back to the deterministic one. And at the end of the day, we sum it all up. So let's go through each of those single steps, step by step. So first step is setting up the system configuration. So here we are just collecting all the matrices that we need. So we take the global configuration of the finite element and the SEA subsystems, and we identify all the junction areas and the specific degrees of freedom for those junction areas. That means we set up the stiffness matrix from FEM. This is our first step. Then we try to find out all the major properties for the SEA subsystem. This is mainly the modal density, the damping, and the group wave speed, which brings us all the information regarding modal density. This is what we need to describe our random or SEA subsystem. And last but not least, and that's the important one, and by the way, the very complicated one, is that we take all the junctions. So we have to find all the junction properties. That means actually finding out what is the free field radiation stiffness into all these connected subsystem with the given physics of the connection. Step 2. Now we set up the system matrices in more detail, specifically for hybrid method, and we identify all the coupling loss factors. So we have in hybrid models, we need both of them. First of all, we have to modify the deterministic part, as mentioned, by all the connected free field radiation stiffnesses. And on top of that, we can reuse them, or some of them, to calculate all the coupling loss factors. And finally, from this, to calculate the SEA matrix. So, good. So what are these steps in detail? First of all, we create the total stiffness matrix. So that means taking the structural one plus all the free field radiation stiffnesses. Then we reuse all those free field radiation stiffnesses to create the coupling loss factor, and from this, the SEA matrix. And then we are in step 3. Now we have to apply external loads. And here I really mean all the external loads that are exciting the deterministic field. That's the first step. So that means we have to define generalized forces for deterministic loads. This could be TBL, random, but also deterministic. And we have to define all the power input into our SEA subsystem. So what power inputs do we have? What is the power input into all our single SEA subsystem in the configuration? Yeah, okay, I just mentioned that. This is just the cross-spectral part of the FE meaning this one, and the third step, that's the power input into the SEA subsystem. But again, this furthermore requires a free field radiation stiffness. If I have a specific force or whatever that's exciting my SEA subsystem, I also need a free field radiation stiff to identify what is the power related to this force input to my SEA subsystem. You see, the free field radiation stiffnesses are kind of key to all the modeling. They are reused a lot. Mainly the trick is to create the deterministic response, or at least the deterministic response in the deterministic subsystem. So the first step here is to use equation 233. That's this cross-spectral excitation matrix as denoted here. We are not using the reverberant loads, not yet. This comes later. And from this, we can calculate the cross-spectral displacement response. And then from this, we know the power input from the finite element system into the SEA subsystem. The next step then is that we solve the SEA equation. When we solve the SEA equation, we take all the power input from the external thing, but also we take the power input coming from the step above. And then we solve the SEA equation from this. And finally, when we have the energy state of all our subsystems, we can, and this is reused in the last step, then we have the reverberant loading back to the deterministic system. And this is used in step 5. And okay, we have solved the and then we used and from this reverberant loading we solve the FEM equation. So kind of redoing this here again, but then using the diffuse field reciprocity. Good. So what is then done next? At the end of the day, we just have to combine all of the results. That means we take the first step is we have to add the FEM results from the external and the reverberant load. So this, if you remember well, that is the very, very first step. We just take the finite element, the total stiffness matrix, plus all the external loads that are not coming from SEA. This is the response of the deterministic subsystem exclusively coming from the SEA, so the reverberant loads. And then we have to, let's say, reuse the SEA results. As you know, this is just an energy solution, and we need physical units out of this to interpret our energy in terms of displacement, velocity, or pressure. And then we are done. So these are the 5 heavy steps of hybrid analysis. Just to be clear, some of the steps could be omitted. For instance, if there is no external loading on our deterministic subsystem, we don't need the first steps. So this is if we have everything. External loads on FEM, external loads on SEA, and we have to combine everything. It could be simplified if one of the loads are not there. In the later sessions, I will go through classical examples where you will learn and understand how this is really done step by step. And by the way, there are examples in my website and on pyva, the toolbox that comes with this book and the lecture, where you can try and play with all those single steps in the real analysis. Good. There's one remaining part about it's a practical thing. I mean, we have defined all the hybrid equations in generalized coordinates. And one of the most important generalized coordinates that's heavily used, especially in structural analysis or in acoustics in general, is a modal solution or the modal condensation. So, and the point is, our deterministic subsystems, they are defined by nature. They could have only a few modes. If they would have hundreds of modes, it would not be a deterministic subsystem. So this is a kind of criteria, but that makes, so in this context, it might really make sense that we use a modal approach instead of the full degree of freedom approach. As you learned from the earlier sessions, all the modal variables are denoted by a prime. And here we see that this is now we are expressing our displaced coordinates by using this modal solution. And then we have our modal transformation matrix, which brings the modal coordinates and brings us back into the to the general classical coordinates. We have this formulation for the forces. This is a modal force, and if we go through it, we can identify and simplify as it was done in the classical modal analysis and use it into our hybrid response calculation formulation, and we transform. That's the most important point. We transform our total stiffness matrix. But there's one very important thing to note and to see and to understand. You see, if we use the total stiffness matrix, we have two components. We have this classical stiffness matrix part, which we know well and which becomes very easy when we use modal condensation. And we have this radiation stiffness part that has to be transformed in the new modal space also. If we do so, we have a kind of modal formulation of this. We have this modal stiffness matrix here, and this looks exactly like the modal stiffness matrix. This is perfectly diagonal. So this is what makes modal systems so useful. Unfortunately, and that's a very important point, unfortunately, the direct radiation field stiffness, it is not diagonal. It's a fully populated symmetric matrix. So that means by putting SEA subsystems onto your structure, you're losing the advantage of modal condensation a lot. This is not such a big disaster. Why is that? There are many methods where you will see you don't need all of them. Some modes cannot radiate, and so on and so on. There are really many methods to simplify this. But in general, you have to consider all of them. And this makes, let's say, takes away a little bit from all the convenient things that you usually have with modal condensation if you switch into the hybrid theory. So this is the reason why modal condensation is not that efficient in hybrid theory, because the direct field radiation stiffness is fully populated. Good. However, all the typical equations like the coupling loss factor and so on, they don't change. They still keep the same form, which is very good. And and some points are, if you just put into it, then it could even more simplified because we are just using the modal condensation and entering the way how the stiffness matrix is described by the modal frequency. Good. Anyhow, finally, not worth very much mentioning, modal coordinates are definitely one example for classically generalized coordinates. And one last remark. All what I've said here is for real coordinates. If you're not using real coordinate system, it could be a wave number coordinate system, then this equation does not perfectly hold. So this imaginary part has to be converted into an other expression. But this is a very specific detail that is not totally required for this session. Just keep in mind, if you use this expression here for line junctions, using complex wave number coordinates, you definitely are in trouble. It will not work with this expression. It has to be modified, as I will show later. Good. So far from that. Thank you for listening and joining this session. I think it was a kind of very, very theoretical, or let's say algorithm-like version, but it's very important because this is really important to understand what is ongoing in a hybrid simulation. So what is the deterministic and what is the random part that is used. Thank you for listening. In the next sessions, I will calculate a lot of coupling loss factors, where you will see and learn how all the single radiation stiffnesses are developed and calculated using various kind of coordinate system, and then how to calculate the coupling loss factor out of it. And this is something that I really like because many other books This is omitted a little bit. And with this diffuse field reciprocity and the hybrid coupling loss factor formulation, it's a straightforward way to explain every coupling loss factor. And this is done then in the next session that will come soon. Thank you so much and see you for the next session. Bye bye.